Our speaker tonight was formerly the chief architect of IBM's DB2 Internet products. He was also the former senior director of engineering at Yahoo. He's got 20 plus years of tech experience and has over a dozen patents in database and related technologies. Please welcome the founder and VP of Engineering Operations for Aerospike, Srini Srinivasan.
Thank you. So it's actually quite a bit of pleasure for me to attend database month here. We're coming here probably once a year or so. And I really like the audience is very knowledgeable and so on. And the double pleasure this time is that events at AppNexus who essentially our first customers. It's also great to see them being in all their own offices. So let's get started. So today I'm going to talk about a combination of ACID and CAP. We go a little bit more into this, but I also want to set the stage as to why this is important. And I'm going to take the example of being in the AppNexus. I think it's very appropriate to talk about real-time advertising. And that's where I've spent a lot of time in terms of delivering, database software to people who have been working on real-time advertising for the last 4 or 5 years. And a lot of these internet-related CAP versus ACID issues have all arisen out of all the work that happened on the internet over the last 15 years in terms of database technology. Things like the DynamoDB from Amazon, Cassandra, MongoDB, the Aerospike. There's a whole bunch of these activities which started with the entire internet requirements as the basis. And what characterizes most internet enterprises, including AppNexus and a whole bunch of other companies, is the extreme stringency of latency and real-time pressure when a particular user is trying to do something on the internet. You want to catch their attention and you want to engage them in such a way that you have that particular user stay on a website, for example. Now, the important thing there is you've got to deal with it at scale, with hundreds of millions, if not billions, of these users arriving over periods of time and knowing enough about each of them to keep them engaged. And that is actually a hard problem. So, if you look at the evolution of internet search, Google, I think, started AdWords in 2000, I think. And that was the first time somebody had actually said there's a context to a search, and they used that for advertising. And then even in 2005, display advertising was pretty much not actually very advanced. People were still buying, bundled up impressions and so on, or going to high-quality websites. Now, Right Media was bought by Yahoo in 2007. I think DoubleClick by Google in 2008. And then I think the founders of Right Media and DoubleClick founded several companies of their own, and including the founders of AppNexus actually. What happened was they all determined over time that the best way to set a fair price of connecting publishers to advertisers was to use a real-time bidding platform and actually build the infrastructure out to make that happen in real time. Essentially, this is a direct challenge to some of the things that Google was doing, and they went about it in a quite different way. They went about it using an open system. You see here a whole bunch of ad networks, ad exchanges, demand-side platforms, and so on. Many of you are experts at this. I won't go into the details of it. And the interesting thing from my experience in Aerospike is we have been kind of working with a lot of these companies who used Aerospike to deal with this kind of problem. Now, why is this interesting from a CAP point of view, right? It's interesting because you need to run your system with absolutely no downtime. And that's exactly at high throughput and low latency. Here are some numbers. I think Gail talked about 2.5 million a second. And that's about several people actually do this today. And what actually happens is, there's one interesting point though, right? When Facebook actually went public, I think it was a few years ago, they had a problem. They used the original Google closed model of searches, and that didn't actually work for them because they don't have the volume that point that Google had. So they invented Facebook Exchange, and this has been a huge driver of their growth in mobile. So this open kind of infrastructure is really important. And anybody who wishes to play in this particular marketplace, be it North America, be it China or India, what they end up having to do is to run systems which can run at very high throughput with very low latency. And the latency is another thing which also got kind of invented over the last several years, is everybody kind of came up with 150 milliseconds or so for an ad to show up. And if you have multiple ads happening on the page, all of this will show up at the same time. And otherwise, you lose the interest. And the interesting thing here is it's a winner-take-all system. Okay, if the ad doesn't show up, then there is no money made. Nobody sees it. In fact, even recently there was this, below the fold, above the fold ad kind of thing which happened, right? I mean, essentially, you want to make sure is the ad really showing up in a portion of the page which the user actually see, as opposed to, you can only determine that from the browser and the settings and so on for a particular user. So you want to actually get it in front of them. If you don't get it in front of them in that time, Google will kind of not call your game, which means you don't get any business. And you can't go down, because once you go down, or even, the interesting thing is, if you think of availability from a CAP sense, it's not like availability is either there or not. It's not black and white. If you would, for example, make your website go 20% slower than a competing website, assuming there's good competition going on, then you can expect to lose 100% of the users. Because everybody goes to the one which is better. It's kind of how Google wants search. So this is all well documented and well understood. So you got to basically run this 24/7, and you have to make sure things are available enough at a good enough SLA into the low latency. Now, essentially the advertising folks are pioneers. Okay, what they have done is created enormous transactions throughput at low latency and made it into an open system where you can actually do real-time bidding across these various components and have various players and build an entire ecosystem, okay, to make this happen. And they all standardize on a simple technology stack. And that's what you need in order to make these kinds of large movements happen. It cannot be complex. So there's an app server. In fact, I think in the early days, maybe like 2-3 years ago, if you looked at the most prominent technologists in this area, they would all have told you that the algorithms they were using in terms of figuring out what ad to serve are all fairly simple. The biggest problem they were all trying to solve was scale. They needed to make sure they can apply these algorithms in volume, okay? Scalability and uptime, and also the SLA, that you capture the answer within a short amount of time, and the low latency were the most important things. In order to do that, you ended up having what you would call an operational database, which can deal with real-time context. And you still have all the batch analytics, which will analyze all of the logs and information that you have of users and make sure that all of that is fed into your front-end database. So this is kind of the architecture the ad tech folks kind of settled on. I'm just going to spend a couple of minutes on showing why it's crossing over, because the whole CAP versus asset discussion is only relevant if you really care about the consistency of the data, in addition to the speed and low latency and throughput. And therefore, I want to paint a picture of what's going on there. Now, I'm just going to pick, this being New York, an example on financial services. So what's happening there is there is a lot of crossover which is happening because people are now used to the internet. One of the people I spoke with in a financial company, I think the CIO, who told me that his own customers were not spoiled because of Google, Facebook, because everybody expects, your basic updates on Facebook to show up immediately, and you are actually used to extremely real-time performance on what I would call as, normal social network stuff, which is probably not as important as your bank account in terms of how it affects you. And what happens is when you have, in this particular use case, is about a securities kind of application where, let's say you made some trades in the middle of the day and you have multiple channels through which you view your account. You view it on your PC, you view it on your mobile or your iPad, on an Android phone, whatever you want to do. And typically what happens is when you start accessing these original mainframe databases which were built like a while ago, and frankly, the mainframe databases everybody says they're up, but they're really not up. They are not distributed. They shut down like what, 6 hours of trading, and they don't actually do anything at night most of the time. So that kind of model doesn't work, and people expect internet level kind of access. They're in the middle of the night, they want to look at it, and they want to get the right data. They don't want to get a message saying the system is down for maintenance. Okay, it's just not acceptable for the people who have been trained on the internet. And they go like, you're managing my money, I want to know where it is at all times. And that is kind of what these people started doing was started implementing caches. And there's a problem with caches. It's a pure cache. A cache, if you have small amounts of data, it works very well. When you have large amounts of, again, this is all about scale. When you have large amounts of data, the cache will fail. Any machine will generally fail at some point in time if you have a running service. So when it fails, it takes a while to reload all the data to get it. So what you can't have is make a trade and then find that your trade is fine. It's actually fine. It sits in some, what do you call it, a message queue, or it sits in some really robust systems. Financial services have all these things. But then what you do is you go look at your mobile device. It shows you yesterday's information because the cache is failed. This is not acceptable. People start getting customer calls and so on. So consistency is now important. That's kind of the point I'm trying to make is it's important to have throughput and low latency, but also consistency. And that's why the rest of the discussion is going to be interesting. So we didn't talk about it. And there are other things. Okay, this is one additional example I want to show. This is social media in China, for example. And we've been having lots of discussions with people all over the world. I just want you to understand that the whole, everybody knows this. There are all these internets which are kind of, some of them are connected, some of them are not, but they're all exploding all over the world. Okay? Everybody has the same problem. Weibo has this problem. And how they solved it, again, in order to solve the problems that they had of high throughput and low latency, they needed technology. They chose, for example, Redis. They modified Redis, they made it SSD enabled, and made it all work for them by keeping track of the latest and greatest technology, but also they had to think through, so on your application layer, you could potentially figure out what kind of data needs to be at high throughput and low latency, and then what kind of data is essentially slower. And then if you can sensitize the application to this particular fact, then you can implement better applications at the application layer. So you don't have to put everything in one database and expect it all to work fast or slow. I mean, that is actually not going to work very well at a large scale, because each of this data in a fast database is large enough that you might want to have it in a separate real-time system. So we see some of this also in companies here in the US like Pinterest and so on. I mean, everybody is solving these kinds of problems. Now, here's where I think things are kind of ending up. Okay? So there's basically a load balancer and app servers, and then there's this in-memory NoSQL, as we call it, where you have a fast key-value access. It can also provide some additional queries and so on, but the real advantage here is to get a lot of reads and writes. Here talk about 1 million or 1.5 million writes, and then 3 million reads. I mean, that's basically what everybody's seeing. Because what you want to do is figure out what a user is doing. Every read actually becomes a write in many cases, because you want to know what they did, what they saw, and that's important. So, and again, you still have your, existing, like Hadoop and other analysis tools. But this is where I think I'm going to talk about the learnings you've had in this layer related to cap and asset. So I'm assuming we'll have questions in the end, right? Eric can ask about it, but if there's anything which you don't completely understand, I'm happy to entertain some questions in the middle also. So some of this is like basic stuff. ACID, of course, A stands for atomicity. And what we are trying to say here is, like, essentially you run a transactional system, it either happens or it doesn't. So if it happens in half, then it's not atomic. So you sometimes what happens is you're not able to complete it, you need to roll it back. This is classic database technology. The C in ACID is not about the same as the C in CAP. C in ACID simply says that anytime you start a transaction, before you start a transaction, things are consistent. And then you do something in a transaction, and when you're ending it, it should be consistent. So if you, for example, adding an entry into the system, and there's a secondary index. So during that time this particular transaction is in progress, you may not be able to find the item that you just added, because the transaction isn't committed. The moment it commits, though, any query on the secondary index is going to find the record, guaranteed. Okay? And that's kind of consistency is what ACID kind of talks about. Isolation essentially is nobody else is able to look at your data while you're changing it. So if a transaction is changing a bunch of items, like for example, take the same example, change the record and the secondary index, you're not supposed to see the secondary index before the record is added or vice versa. So that is, you isolate yourself with respect to other transactions happening in the same set of data. And again, you have various levels of isolation, which is kind of defeats the purpose of what I just said, which is like you allow people to read dirty data. If you want performance and you can deal with it in your application, you can get data which is inconsistent and go for it. But it's really not something I personally would recommend for ease of writing applications. Because there are some real costs to having your application dealing with some of these core database issues. And the last one is durability, which is probably the easiest to understand. Once you commit data into the database, you should be always able to find it. It shouldn't go away because something, a machine failed, or if you can't reach it, that's a different point. We don't know. But the point is, if you can reach the database, it should give it to you if you're going to do it. That's a guarantee of durability, which is really important because you can make real world, the classic example is, you put money in your bank account. You don't want to make sure that somebody on a machine in the bank died and then your money's not there. Those are the kinds of things which, and there are many such examples of it. It even happens in, if you're counting clicks and so on. You just don't want to count it wrong at the level where real money is involved. Now, in terms of cap, I think this is, and again, we talked about paxos and so on. So, the cap is essentially something which comes, becomes really important in distributed systems, of the sort I talked about. Real-time advertising we talked about requires systems which essentially have to run at scale all the time. Okay? So, what happens is when there's a failure of the network, of the machine, of even the software, you really need to have ways of characterizing what exactly is possible in a certain system. Because if you would know if a system can basically provide consistency in all cases, then what the cap theorem talks about is you can't actually produce it if you, for example, have a network partition of a cluster system. If you have only one node, it's very simple, which is the classical ACID kind of concept. Right? But here, what we're talking about is, I'm sorry. So availability, of course, the gap in consistency is that copies of the data have to be the same in distributed system. It comes into play. That's one example. This is not something ACID actually talks about. And therefore, the availability is pretty obvious. You need to have a system to be 100% responsive at all times. However, there needs to be a specified SLA when there's a failure. And it needs to be a small amount of time. It cannot be that a cluster machine is going to take half an hour for it to come back online. That is not satisfying the availability requirement. On the other hand, if you say, at the time the machine fails, for tens of milliseconds, there's going to be some errors returned, and then it's going to, restore itself based on the copies it has, that's actually acceptable. Partition tolerance, this is the hardest one, mainly because, but there's also an escape I'll talk about regarding partition tolerance. When you have a distributed system, you have, if you set it up over a wide area network, then by nature of the fact that it's a wide area network, there's a delay. If there's a delay, then there are probably different kinds of failures that can happen with these various items that exist geographically apart. And that results in potentially, inability to tell from one component system whether the other side of the system is up or down. And you don't know, there is no SLA as to how long is it going to take for me to figure out for sure. If at all, it'll be too long if you want a low latency system. Okay? So that is essentially, if you want to be tolerant to partitions, what that means is you will end up with what's called a split brain. You end up with two subcomponents of the system, both of them potentially running, but only one of them, together they have all the data, but subcomponents may not have all the data. At that point, do you want to provide full availability, or do you want to provide full consistency? It becomes an interesting question. Okay? So that's kind of what the cap theorem talks about, is you can't actually have all three satisfied at the same point in any distributed system. Okay? So, and what exactly it means is, if there is a network partitioning happening, the system has to choose either consistency or availability. You cannot have both. And that's kind of the main thing there. I already talked a little bit about it. Is there a question? Okay. So the same asset is not exactly equal to the same cap. So, in theory, right, definitionally, asset is possible in distributed systems, but it doesn't actually help anybody. So you really need the C in cap to make a system which really runs well at scale. So, we can have an interesting discussion over it, but it's moved. A little bit about, our own example that we've had in our project on these topics. So, when we, in terms of, you have to make choices. Okay, that's the other thing I want to let you know. You cannot have everything. If you want to have really high throughput at 2 million, 3 million a second, like we talked about, and you want to have a low latency of under a millisecond, you cannot probably do a distributed system which has nodes, one node in San Francisco and one node in New York. Okay? It's just not going to work because just the speed of light and what happens over the network is going to kill you. It's going to be 80, 90 milliseconds. Even the Google scanner effort has tens of milliseconds in terms of transaction habits. But you can actually do something there. You won't be able to get that low latency you need for your 150 millisecond ad service, for example, or even for that matter, consistent behavior in the financial use case that we talked about. So what you end up doing is you essentially have to make choices. And there are some choices, for example, Aerospike has made that we talked about. For atomicity, right, we actually deal only with single record atomicity. We do not actually, at the application level yet, can do multi-record transactions. It is not hard to do, it is well understood, but it will cost time. It's something you have to give up for. And then, of course, you need to support, atomically changing the data and the index at the same time. So there's really some internal multi-record stuff going on, because you don't want to just have a simple primary key-based key-value store. That's actually useful in itself in many cases, but then you don't become more general-purpose applications. So if you are going to do secondary indexes on it, you need to make sure they stay consistent and not make all the changes to it. So the problems we solve are fairly complex. Now, in terms of consistency, we don't actually do RDBMS-style constraints. Most of them are implied constraints, like the ones I talked about, secondary index being in sync with the data, multiple bins in the same record being kind of, having exactly the same result when you change it. You can do multiple operations on the same record as part of as part of an update. You want to make sure that all of that is correct. And then of course you got the whole idea of isolation. You just use loss.
What is bin?
Bin is just a column. Aerospike terms of column. A column in relation databases is extremely restricted in the sense that you have to define the schema before and so on. So we just use it differently. It's really a column, but it's flex schema, so you can two records in the same table. One of them can have a column with a name to be integer, and the next one would have the same name with a string or even a list. So it's flex schema. Then durability, of course. You got to make sure that your data is safe in the system. Now, you can do durability multiple ways. Writing it to persistent storage is not the only way to have your stuff durable. If you have multiple copies in an in-memory database across multiple nodes, you can actually prove at some point that if you have enough number of copies, then it is actually as durable as potentially putting it to a persistent storage. So, we use both. We basically use SSDs. We also use multiple copies. So we use both persistent storage and we use multiple copies of memory. I think together we can provide a really robust and durable system, which is as durable as anything else you have. And then you can choose how much more you want based on the number of copies you store in the systems. In terms of Aerospike, or in terms of any system actually, what exactly does consistency mean in CAP, right? You've got to change the copies of data in the system synchronously. So this whole concept of eventual consistency is basically not an ACID concept, right? It is essentially the concept that you change some data in the system, and that data is not being read by a subsequent read. Okay? So one transaction comes in, it writes some data into the database, it succeeds, it goes away. And then the same client potentially can make a request into the database for a read, and it may not get the latest value. That's exactly, if there's a failure, there's no failure, it's all going to be fine in any system. But if there's a failure, then you should be able to find the same data you committed before. Right? If you don't find it, then it's called eventual consistency because you found something potentially used earlier. And the way I think, our philosophy has been that you want to always find the latest data. You can, of course, relax it. So if you implemented something which had full consistency, you have the ability to tune it down. If you don't implement the full consistency, then you can't actually tune it up. You have to rewrite stuff. Availability, again, is, okay, so let's just take the case where we avoid partition tolerance. Okay? There's no partition tolerance at all. I mean, let's say no partitions are happening. Even then, to maintain availability and consistency in a distributed system is hard. The only thing is, it's possible, because it's not proven enough. Okay? So that's kind of where you should look at a lot of the algorithms we published in BLDB at some point. A lot of our algorithms in Aerospike have to deal with how to provide availability and consistency in the absence of network partitions. Okay? If the network partitions happen, then the choices we have made, originally was to make it an AP system, so we're more available and consistent. If you're going to be consistent, you've got to turn off availability. And that's something we're doing. There are choices you can make. So for internet applications, right, like real-time bidding we talked about, I think AP or plus eventual consistency would be better than having a CP system, which is consistent and partition tolerant, and then reducing availability. Because if you can't run your business at all, and remember, right, all of these we're talking about is going to quickly come back together. Because you want a system which is essentially, when there's a failure or whatever, can quickly recover also. So there's a performance issue. It's really a latency availability issue. So you're just saying, I want things to be available. I don't want to wait. It's not like it's going to be down. I don't want to wait the extra 30, 0.3 milliseconds or 0.5 milliseconds to get the real data. Because I may have to look at multiple bases of the cluster. So you can tune it up, and then within another, and then it's fine because it may be okay for real-time bidding kind of internet applications. For enterprise applications, it's not going to work. Because availability is going to be important. You made a trade, it doesn't matter like it was a millisecond later or less. You want that to be persistent. You want to get it all the time, and it doesn't matter. So in those cases, I think the user may be actually okay with saying, you know what, don't give me the wrong data. So those are the choices you have. Right? And what actually saves us are a bunch of things that Professor Brewer talked about in a 2012 paper, okay? In a 2012 article, and we've actually been working on this for since 2008 or so. So we kind of independently come to some of these decisions in distributed systems, and I just want to give you a flavor of those. One of them is, first, because partitions are rare, right? There's little reason to sacrifice either consistency or availability. Okay? And how do you do that, right? You basically figure out how to make partitions rare. So to some extent, you can make partitions rare by making sure that heartbeats are easily detected, or their absence is also easily detected very fast. Okay? So if you, for example, the deployments that Aerospike runs with, all of the servers are essentially typically in the same data center, potentially in the same switch, appropriate fail-safe things can be implemented. So the heartbeats are going within milliseconds of each other. So and again, going back to the backsource point, so backsource is, in the general case, not terminating, because if you had some nodes of the cluster far away and some of them close to each other, it is not possible for the entire cluster to determine in a reasonably small amount of time whether the cluster is full or not. Okay, and this is a problem because the node will come in and then it will go out. Where will you set it? For the nodes which are close to each other, you don't actually have to have more than maybe like 5 milliseconds. The nodes which are like in San Francisco, the other one is in New York, you need like 100 milliseconds. Now you've got a real problem. You don't know where a node is in or where a node is out. You can't have it, or you slow everything down to 200 milliseconds or something, which is not acceptable, right? Because the whole idea of having low latency is it is within the time that somebody can show something at the human level, right? Which means that there is you don't have any leeway. I mean, we're not getting any slower, we're getting faster or anything. The younger generation demands even faster access, not slower ones. So that's kind of the idea there, is to then keep everything close to each other. And then Of course, you can do other software things like, have dual channels for heartbeats. Don't let clusters kind of go apart easily. Okay? Make sure that it doesn't happen. So if you do all of that, and then you use the access algorithm, it will actually coalesce very fast. It's based on how fast you can detect. And if you can detect it fast, then you can coalesce fast. And then, what do you do when things fail? How do you figure out consistency? Right? You can do a bunch of algorithms which are pretty kind of involved, but it's possible for you to kind of figure it out. So that's kind of what just to show you an idea. What we end up doing is you slice and dice it differently. Okay? Essentially, you have closely coupled clusters, and then you do asynchronous application across geographically distributed things. And this actually matches quite well with the kind of applications I talked about. And you'll get enough, it's very rare. This one will not partition. Usually what happens is you lose the entire data center. Okay? Because some switch or something blows and the whole cluster goes away. It's very rare, even that we haven't seen that much of. But the point is, now you have a way of thinking about it and building applications. Then there are some other choices you can make, right? So you don't actually have to have every subsystem in your cluster decide on C versus A the same way. Okay? I'll give you a couple of examples, right? You could basically, essentially there's a data path, right? One thing we have to do in a clustered system in which you can add capacity on the fly is you need to be able to do data rebalancing. When you're doing data rebalancing, it will impact in terms of resources, whether you can do individual reads and writes or not. Now, what happens then is, if you have, this is the point I was trying to make earlier, which is now that you've added some nodes, it could be that you're doing a rolling restart, you're getting copies of data in the system, which need to be reconciled, so to speak. So when a read comes in, this is the eventual consistency problem. You already written to the cluster. The cluster has now added a new node. It's maybe got some old data in it. Now, any read coming after that will get slowed down if it has to be consistent. Because it has to look potentially at two nodes to see which of those two is the right data, which is the latest one, right? So there is an effort involved in doing that. And it is possible that you don't want to expend the effort. You can live with the old copy, which is the real-time bidding case I talked about. People could live with something which is like a couple of minutes older. On the other hand, in the securities example, in your account, you're not going to do it. You're going to spend the extra 10 milliseconds to go look at these 4 copies and get the right value. So that is a choice you can make on that subsystem, which is basically how do you do reads. Or you could simply, these are the 2 choices you have here. You could disable the repeatable read so you can get an eventual, an older value. Or you basically do the thing, you go read the multiple copies. It takes a longer time, but it gets you the right data. The other thing you can do, and this is something which is very interesting, cluster state trade-off. I talked about heartbeats. So you can only do this if your heartbeats and your cluster nodes are close to each other. Okay? Heartbeats have to be really fast. What you can then do is you can mimic a complete cluster outage for 10 milliseconds. Nobody actually notices this. You're going at a million, and then the cluster coalesces, right? The moment it is there, you know exactly where every data is. The few milliseconds you need is merely to figure out where everything is in the cluster. You're not moving anything. But you can only do that if you can determine within a very short amount of time if the node is in or out of the cluster. Again, it goes back to that. So now you can actually, what you've done is you have actually traded off consistency for availability, right? You basically said, I'm going to be consistent, I'm going to be minimally unavailable to make sure I am maximally consistent. You can only do that if you make a bunch of other assumptions around it. And that's important. So it's good that these things exist because otherwise you wouldn't be able to run systems at scale which stay up all the time. Because failures will happen, nodes will fail, switches will fail, data centers will fail sometimes. But through all of that, you need to be able to run your business and run your systems. Right? And we're not breaking any cap theorem here. We're simply saying we're just exploiting certain things based on the way our systems are set up. And that's a choice one has. Okay? And clients won't notice this because you put, and the other smart thing you can do is make your client smart, intelligent, so to speak. So it understands where data is in the cluster. Which means that you place less load on the cluster during these events, which kind of stress it out. a little bit on this. I mean, essentially, if you look at what we do, you take nodes and you add a node to the cluster. I already talked about it. The cluster automatically discovers it. The new node arrives. In a very short amount of time, all these 4 nodes agree where everything is. That's important. It has to happen really fast. The backsource doesn't terminate if it's not short, so the short heartbeat makes it happen. Once that happens, the backsource code finishes, then the partition migration is scheduled immediately. The data is still wherever it is. The client is smart. I don't have a slide for that, but the client is smart, so he immediately knows where everything is, so it starts redirecting data. And that's where the other stuff comes in, the repeatable read issue. Now, I can say that if the data, can I allow, a read to happen if I find any copy? Just have a setting. Say yes, and then the first copy I get for that data I return. So you have lower latency. On the other hand, you say, no, I want you to look at all the copies of data in the system for this particular record and give me the latest one. If you do that, it'll take a longer time. Only during the time when this whole migration is going on. Because once it's finished, it's finished. It's in the right place, then it's as fast as it goes. So those are trade-offs you make during this. And you do this atomically, right? I talked a little bit about ACID. I mean, atomicity is not just for individual record reads and writes. It's also for the migration of a partition from point A to point B. So you got to make a trade-off, right? You can't obviously shut anything down, so there are some additions. The trade-off here is I do more work. For example, during some portions of the partition migrations, writes are sent to both partitions, which you don't know which one is going to be active for a short amount of time. And then once the partition is really moved, you stop writes on the other one. And then we throw it away. Some writes could have been wasted. But that's okay. You just traded off some effort for availability. And so you didn't try to shut off the partition at all. Because otherwise you have to lock both and make sure that whatever time it takes, maybe it takes, let's say, 1 second to do the cutover, you have to lock it. And that means for that 1 second, all writes to that partition will fail. You don't want that, right? If you're going to do availability. So you do extra work. So and that's kind of what we do. Again, that's not anything to do with the cap theorem itself. But just getting consistency and availability in itself, even when the cap theorem is not violated, is hard enough. A couple other points actually. So you can actually trade off these things. I think I've already talked about it a little bit. And again, you can look at all copies. It's not like you don't have availability. The way it will manifest itself is it will take longer to get the consistent data. It's still there. Then tuning the heartbeat, right, is really important. Increasing the application factor. Right? You can basically make sure that if you, for example, wanted to do, and this is one use case which came up. So if you wanted to do a join, okay, of a large table with a small table, it is possible for you to do that even in a system like ours, right, or any system for that matter. If you keep the small table in memory everywhere, okay. So you can make choices of using more resources in order to provide, better kind of outcomes. And that's something you can do. You can also do write all copies. So essentially, if you want to actually not write every copy, if you can live with some level of eventual consistency, you don't have to synchronously write everything, all the copies in the system. You could write one and then let it go. But if you're looking at it should allow you to tune these. If it's going to tell you up front, this is the only thing you can do, that's probably not going to be a long-term choice you can make unless you know exactly what application you're working on and you will never need that feature again. Then that'll fit. High performance is important, okay? A lot of this can actually be, I would say, mitigated or reduced. The impacts of these issues can be reduced if you had extremely high performance. And this is one thing that actually, people ask me, why is it that, we actually publish, things about how we are faster than others. It is not the high throughput, low latency that's important in itself, because nobody is actually going to run that many transactions. Like we can run 1 million per second on one node, and you really need it. No, you don't need it for your application reasons, but you need it for operational reasons. If something bad happens in the system, the extra capacity that is there in each node is what enables you to continue to run the 2 million in the cluster without actually making any of your individual nodes go out. That's important. So you can tune it. High performance, faster heartbeats, all of that is actually very important. And what high performance also buys you is it buys you smaller clusters. When you have smaller clusters, you can actually do this better. So vertical scale is as important as horizontal scale. and you have choices, okay? And you can make that. I mean, one of them, I think, is, you can basically provide high consistency in AP mode, right? And the way you do that is avoid the need to sacrifice consistency by minimizing the formation of network partitions. So if a network partition happens in a system like this, which you have, which you want to run, you need to shut down the entire cluster. That's the only way to kind of make that go away. So you run multiple clusters, you can actually deploy that. It'll work. On the other hand, you may say, you know what, I don't want to do that. I don't want to have all this, deal with that. I want to actually run it in CPU mode. So what that means is I'm willing to live with some level of unavailability. So if you, for example, lost 2 nodes in a cluster, which has only 1 copy of data, there's only 2 copies of data. If you lose 1 node, everything is still there. If you lose 2 nodes, you're going to lose some of the data, right? So what you can do is for data which you don't have, or partitions, I didn't talk about how Aerospike is partitioned, but it applies to any system. If you do a divide and conquer algorithm, you find some data is not available fully, then you can simply say that I will not allow writes for that portion of data until it comes back up. Or that actually works. So what you've done is you've not made the entire thing unavailable. You just made sure that the small portions of data which are not, which you can actually maintain consistency for, you simply block writes to it. Right? So you could do that. So those are choices one can make. Then basically you have to sacrifice. The key point that is how much availability can be, are you willing to sacrifice to maintain consistency? The other way people do it is they allow availability and they compensate for it later. You can do that too. You can just allow writes to happen everywhere, and then you say, you know what, within half an hour or so, when the partitions come back up, with an SLA, I'll clean it up. That's fine too. And then what happens is that subsequent request later is going to essentially have to deal with it. So you could make those choices whichever way you want. So you will have eventual consistency in a way, but you will have full availability. Again, you can basically trade off these things in any system. In terms of nodes on Aerospike itself, I think this is how we run today, and this is something we will do in the future. So there's no reason why a particular database has to be only one way. These are just problems you solve, and these are things that users should be able to pick on the deployment. That's kind of the idea I'm trying to talk about here. It is not a one way or the other. These are choices people should be allowed to make. And I think that's pretty much brings us to the end of this presentation. So this is, a lot of this information is there in this article by Brewer, and then we actually talked about our development for a while. We have some basic goals, right? Our goal has been to not sacrifice consistency just because things have to be available. We try our best to keep as much consistency as possible and as much availability as possible. And then what we have found in practice is you can actually do pretty well if you make certain assumptions with the hardware and the networking, with all the features that are available today. You are able to make those trade-offs and push the envelope, so to speak. And that's I think the most important thing I have learned personally in this. We of course, because we've been working on this for a while, we've discovered exploited some of the flexibility available in the CAP Theorem, and Brewer talks about it in 2012. We've been using it for a couple of years before that. You can actually achieve very high levels of consistency, availability, and performance in a distributed system. I think Aerospike is also now open source, so you can actually download and check it out to see how these algorithms work. So it's available for you to, we're more than happy to have you contribute and improve what we've done. Thank you.
I just wanted to remind everybody we are giving away Beats by Dre headphones. Does anyone know where that basket is that we passed around earlier? There. Could you just send it around one more time? Just drop me your card. Yeah, Bill Laura. Just drop your card in there, or if you don't have a business card with you, then you can write your name on anything. And let's get started on the Q&A. Who's got the first question? That hand right up there.
Choices of so many different questions. Maybe the first one would be, from what I understand, you have a very tunable system that allows you to make a lot of different trade-offs based on your need. The more flags you have, I can imagine, the more different combinations of things you need to trad and experiments internally, just to be able to see how the different combinations work. So I'd be interested to know if you could share anything about how you internally handle and test and verify a system that has so many different topics.
That's actually a great question. And the question was about all these options that you have for tuning. Now, I will tell you this though. We actually don't allow, even though the knobs are available, the experimenting is typically done in the lab. It is not done in production. So we know exactly how things are, and a lot of it is actually, you can think through it and say, so it's not like we're trying to turn the knob and find out how it's going to work. It's more like, what knobs do we really need is where most of the discussion is. Because adding a knob, to your point, is extremely critical, because once it is there, people are going to use it. So you don't want to add any knob in our product. What we have experimented with is a lot more than what we have released up, let's put it that way. And I think the key things are, I think it's all classical database stuff in some sense. You do the one default is, it is the most consistent, the most available, right? And then you have the AP or CP flag, which we have not added by the way yet. We know, we've had it in a site branch, but we've not added it, because you've got to really be careful about adding those. So my answer to that is, yes, we have to be very careful. And we try not to add too many of those flags in those areas.
I have 3 questions. The one slide where you showed like a different data center for Texas, Amsterdam, right? Can you actually tell us like, okay, how does a different data center, different clusters communicate with each other? Like you mentioned there is some asynchronous communication happening there.
Yes. Yes. Okay, this is the one you're talking about?
Yeah.
Okay, so the question was how these clusters communicate to each other. The way we think about it is very simple. There are pieces of data, typically namespaces or sets of tables, basically, which can be replicated across data centers. Each cluster in these data centers would have that namespace. So there are 4 different kinds of circles that are shown here. Color is not very clear, but the point is there is one global data which is shared across all 4 data centers. And there is one which is shared across just the US data centers. There's one between the European and data center in Ohio. So those can be configured. And the actual way it works is a simple log-based algorithm. So what you do is you log the transactions on the cluster where it's happening. It knows where the configuration of where that particular data has to be shipped. It could be multiple potential targets, it could be a star schema or a ring schema, whatever. And then the system simply reads this log, gets the data from the database, local database, and ships it out. And it ships it out just like a normal client would. So there's nothing special. So you could have one cluster with 10 nodes communicating through this mechanism with a cluster with 12 nodes or 5 nodes. And that capacity has to be correct.
So does actually one node only communicate with, or like every 10 nodes communicate with the other?
Every client, so each node in this model, in one cluster, the source cluster, let's say, is a client to the entire cluster on the other side, which means each node has to be able to communicate with every individual node. That's kind of, I didn't talk about that a lot today, but the Aerospike client can talk to any specific node in the
So the one or 2 questions are like, say, sorry, does actually write happen to the master node? Like there is a master node assigned, and then write happens only to that master node, and then from there it goes to all the one. And the one more question is like, say, I saw your numbers like you are like 10 times faster than like so and so teams, right? How and why is
Let's
that?
limit to one question. Is there other people? We will have time for more questions afterwards. So let's just call on time. Just to give a heads up so you don't feel like you're holding on there. Srini will be here for one-on-one questions afterwards, so everyone will have a chance, okay? Next question, please. Yes.
So you didn't really go into too much detail about Aerospike's architecture specifically, but just from the top, it seems like it's fairly similar to Cassandra. It's a gossip protocol, and there's no master slave, but it's just every node is applying itself. So like, how is it any different from what Cassandra architecture is?
Actually, Cassandra is a good example. Yeah, it's one of the philosophies I talked about here from the Dynamo people. This is what Cassandra is based on. So having identical nodes. The key differences are the way we do partitioning and predictable performance. So what happens is, Cassandra has its own, it scales really well. They're not focused as much on vertical performance, individual performance. And they have pretty much do eventual consistency. The kind of things we do is when you write to a master in a cluster, the master coordinates in a very short amount of time transactions across copies. So performance is one, predictable performance basically. We can do 1 millisecond. Cassandra is typically at 20 millisecond range. That's one big thing. And the other one is the consistency part.
Yes, Nick.
Can you talk a little bit about Aerospike's implementation as it regards to the C and ACID consistency between data written and the index? And because we didn't talk much about your querying abilities and how you pull data out of the system and the lag time perhaps between writing data and writing index.
Yeah. It's a great question. The question is about how indexes and data and how do we keep things going fast. This was not specifically an Aerospike talk, so I didn't more talking about general principles, but here's how we do it. Okay, our indexing mechanisms, we build on our original primary key mechanism, which scales very well and is high performance. What we do is we build the secondary index on every node. It's a scatter, gather algorithm. So when you run a query in Aerospike, you have to send the query to every node, it's a secondary index query. And then in parallel, it executes on every node, gets the data back. So since every secondary index that we create is created on every node, we can actually keep it fast within the same node. And we keep the secondary index today purely in DLAM. We do not put it on this. So that gives you speed.
Time for one last question. Yes.
We can have a discussion later with a lot of concepts I just said.
Based on the presentation, would you consider Aerospike as a mission critical database platform, or is mostly a fast execution? What have been the
So Aerospike is, you can call it as a mission critical platform because that's the only way our customers use it. It has to run all the time and the business depends on it. But it's also about throughput and latency. It's both actually.
Okay, for our Beats by Dre headphones, Solo 2s, they've asked for a volunteer. You look scared, so I'm picking on you. Could you just mix them up, please?
Sure.
Okay. Now look the other way and reach in. Grab one out. Read it.
Chow Chen Chen.
Srini V Srinivasan, thank you very much.